Let me get started. I'm going to take a spin and kind of talk about some of the latest trends in wireless infrastructure, an opportunity, and pivot this to ORAN specifically, which is one of the initiative that has been launched to try and standardize and improve the efficiency of the networks. But before we even start at ORAN, I want to just remind everyone about the overarching vision that IMT 2000 had for 5G and the use cases and the features. As you can see here, there is a lot of information on this slide, but mainly what 5G is supposed to bring for us is a much higher data rate and user experience associated with it. What it is also supposed to give to us is improved capacity with features such as massive MIMO, as well as enabling other spectrum that I'll talk about. And most importantly, improve latency so that use cases that were not previously thought of could be enabled with the extra data rate that is available and also superior latency. Before I talk about the slide, let me get my pointer on. As you can see here, I alluded in the earlier slide about massive MIMO as one of the distinguishing feature, which enables higher spectral efficiency for 5G. And massive MIMO can come in two different forms, whether it's digital beamforming or hybrid or analog with digital beamforming combination. I'm not going to delve into too many details of that. Elsewhere, you can find information on it. But the spectrum has also been expanded. There are a lot of C-band spectrum that we all heard about in the 3.4 to 3.8 gigahertz and 4.2 gigahertz, and also the 6.4 to 7.125 and 104 bands that have been opened up, with what we now call as an FR3 bands, which is kind of nestled between the FR1, which is the sub 7 gigahertz, and the FR2, which is a millimeter wave, that is opening up to improve capacity. And as we go more towards 6G, at least one incarnation of 6G for the future would be in extremely high frequencies, even much above 100 gigahertz, to enable sensing and other use cases. Okay, let's come back to ORAN then. And what exactly is ORAN? This is an alliance formed from a while back in 2018 by combining multiple forces which were trying to achieve the same, the XRAN forums and the CRAN forums and the previously TIP initiative. And the goals of ORAN are pretty simple. We need to make things open and interfaces between various RAN components. Again, RAN stands for Radio Access Network, to be standardized so that we can do mix and match of various hardware for the radio unit and the distributed unit and the centralized unit I'll talk about. And also enable use of COTS hardware instead of proprietary hardware. And by standardizing the APIs and software, we can enable a lot of innovation and standardization and resort to open source where appropriate. Why is this important, right? Clearly for the operators to reduce the CapEx and the OpEx on maintaining their network is essential. What this will do is by providing an open interface, we can improve competition and enable innovation with more players coming in and not kind of limited to certain players who are able to control the entire infrastructure, right? And also by making this cloud native, we can enable more scalability across all platforms, and this will enable further agility in the system and in the network and enable various features like what we talk about, radio resource management, and improve network performance by real-time closed loop controls, and enable software upgrades for improving new capabilities or importing new capabilities thanks to the cloud native infrastructure. The membership is quite comprehensive. I mean, if you go to the ORAN website, you can download all of these information that I'm showing here. Pretty much all the big operators are part of the ORAN alliance, as you can see here, from AT&T to Verizon to T-Mobile to Dish Networks to Reliance Jio and Airtel, Rakuten. Everyone is part of the ORAN alliance. Obviously, the operators stand to benefit a lot based on the goals of ORAN. And when it comes to the contributing members, pretty much everybody, including the OEMs who are developing the hardware, such as Ericsson, Nokia, Samsung, ZTE, a lot of the component vendors like Renesas themselves, as well as a lot of research institutes, are all part of ORAN. So clearly there is a lot of momentum behind this initiative. However, there are quite a few challenges for ORAN, and some of you may have already realized some of these, as I was mentioning about the various goals of ORAN. The main challenge that would come when you set up a open RAN system is troubleshooting and end-to-end ownership. When you have a mix and match situation where you have different companies providing the hardware for various components for the RAN, then how can the operators make sure that there is end-to-end ownership? And when the things don't go well, how are we going to troubleshoot? That has been one key challenge. And also related to this, there is whenever there is standardization, right, there is also performance limitations that come with it, because now interoperability means you have to go with the least common denominator where everyone can agree on the interfaces. Things like uplink boost and various features such that can be further optimized by a particular vendor innovating on both sides of the fence would not be allowed if we have to standardize the interface. So that is certainly a limitation when we want to implement ORAN systems. The other one is the other point is the current incumbents. Of course, this has now not been an issue anymore, are disincentivized because, hey, if they have the entire RAN system, then what exactly have they got to win by doing this open RAN? But I think credit has to go to all the OEMs. They have embraced this particular initiative and have really supported. Even more lately, we have seen some news coming out of the AT&T and Ericsson deal, where Ericsson's going to provide open RAN compliant radios to Ericsson. And even as one of the purported goal of ORAN is the hardware and software cost improvement, actually this could as well be a challenge, because just taking an example of Renesas, when we provide RF components to our customers, which in this case would be OEMs, volume breaks come into picture, right? And when there are only a few players, their volumes are higher and they are able to command lower hardware costs when it comes to getting components from their vendors. The same can't be true when there are yet too many players, and then not each company is able to demand high enough volumes from their vendors. And similarly on the software, right? And going back to the troubleshooting and end-to-end ownership, somebody has to pick up the tab to make sure that all components of the RAN are working together very well. There is a lot of overhead on software there as well. With the ORAN out of the way, I want to spend the rest of the talk. Hopefully we have enough time to talk about these things, about the various architectures and interfaces for wireless infrastructure, especially the focus on ORAN. When you look at the RAN access network logical split, right, and some of you may have heard of these names, or I may have already talked about them. So RU, which stands for the radio unit, is on the tower top, very close to the antenna, or sitting right next to the antenna. And what we call as a front hall, which is the network interface to the next component, which is the distributed unit, and then the centralized unit. In some cases, the distributed unit and the centralized unit may be combined together. And the goal is, like I mentioned earlier, to make the DU and the CU with COTS hardware, whether it's x86 based or ARM based processors, and make them abstracted so that to a level where you can control this with software and make this cloud native to give complete flexibility for various type of implementations, and using this computing platform as a collection of these infrastructure nodes, right? And of course, the backhaul is the connection through to our core network, right? And sometimes the connection between the DU and the CU is called as the mid-haul, but in more cases than not, the DU and the CU may be combined together. In the interest of time, I'll go a little bit faster on some of these slides, but this is how 3GPP defines these various splits, because I will be talking about some splits as we talk about some ORAN specific implementations. And as you get closer to the RF, which is closer to the antenna, the split number increases. The split is nothing but a logical way of saying where maybe a RU and the DU may be separated, or the DU and the CU may be separated. And we can see in many cases, the RU and the DU are split based on option 7 or option 8, and CU and DU normally are around option 2. And specific to ORAN, we can see that there is a very popular split, which is called as option 7.2x, where all the RF hardware from RF front end and the digital front end comprising of functions such as digital up conversion and down conversion, CFR, DPD, as well as some low-level lo-fi implementation of FFT and inverse FFT and addition and removal of cyclic prefix and patch functions are inside the radio unit. And the DU will have the pre-coding and most of the real-time aspects of the RAN functions, including the Hi-Fi and the MAC. And the CU normally has the RRC and the PDCP, or the non-real-time functions of the RAN. This is kind of what I mentioned earlier, where we have this front haul and mid haul between RU and DU. And on the RU, we have all the hardware from the RFFE, RF front end, power amplifiers, LNAs, transceivers, and the lo-fi implementation. And when it comes to the DU and CU, the various other functions on the MAC layer and the higher level PHY come into action here with implementation processes using x86 or ARM-based platform, and also the timing synchronization done with IEEE Sync E. Okay, coming back to Renesas. Renesas has solutions for ORAN or wireless infrastructure across many of our product lines that we provide to our customers. We have on the RU and the DU side, power, timing, RF and microwave, and optical interface components. We do have our power timing and memory interface when it comes to the DU and CU implementations. And same thing on the interface, we have optical interface and backhaul RF components and microwave components. And when it goes to core network, a lot of our power timing and memory interface products are to be found in the core network as well. I do want to spend more time on the RF front end and close to the RU, because that's where a lot of innovation can be done. And if time permits, I want to spend some time on some of the areas where innovation can benefit the RAN implementation in the future. Like I mentioned, on the RU side, on the radio unit side, uh, the RF business unit that I represent at Renesas, we have built a comprehensive portfolio of parts, FR1, LNAs, VGAs, pre-drivers, RF switches, PA modules, and FR2 millimeter wave beamformers and up-down converters for 5G millimeter wave. And we also built some reference designs. This is an example for an FR1 based reference design with all Renesas RF components, from pre-drivers to LNAs and switch plus LNAs, as well as now we have our PA module portfolio and bias controller portfolio. So pretty much all the RF components, whether it's FR1 or FR2, are available inside of the Renesas RF business unit now. This is a millimeter wave 5G or FR2 demonstration panel reference design. As you can see here, a massive MIMO. This is particularly a small an array, which is an 8x8 array that has been implemented as a reference design with our beamformers on the backside of this antenna array and our up-down converters and the synthesizer for the millimeter wave frequency. All of these are getting a lot of traction across our customer base, and the performance, especially of our PA modules and the millimeter wave beamformers, are state of the art, pushing the boundaries. I kind of mentioned about scalable solutions, and moving beyond the RF front end, I want to go look at the transceivers as well as the RU SoC, or the baseband on the RU side. And this is where the implementation can be done in ways that the solution can be made extremely scalable. When it comes to the transceiver, there's a lot of the lo-fi as well as the DFE function that I mentioned that can be put and kind of abstracted to a level with software and firmware control, so that you can turn on and turn off functions, as well as optimize the performance depending upon how you want to trade off between performance and power consumption. And also with the latest chiplet-based architectures, you can set these up in such a way that depending upon whether it's a small cell implementation or a macro implementation or massive MIMO implementation, you can populate your package with various chiplets with interfaces that are high-speed digital interfaces such as UCIe, so that you can make this extremely modular for allowing scalability in the implementations. This is an example of a direct sampling transceiver from one of our partner companies called Jariet. Extremely high sampling rate, 64 gigasamples per second, where everything in FR1 and FR2 and even FR1, FR2 and FR3 bands can be all pushed into first Nyquist. And some of these technologies that I'm following, whether it's Jariet from elsewhere, are showing that the direct RF sampling is not a myth anymore, and we can start seeing systems, even high performance systems like wireless infrastructure, with direct RF sampling implemented shortly. Of course, the RF front end will still be there with the LNAs and the PAs, but the transceivers are moving from zero IF or low IF or heterodyne architectures towards direct RF sampling. Last but not the least, I want to leave all of our viewers today with some ideas to go away with on how we can innovate and bring more value to RAN implementation, especially around the radio unit. Higher IBW, instantaneous bandwidth for multi-band applications, broadband implementations of the power amplifiers with very high linearity are extremely valuable as we go into the future. Making modules so that they're all plug and play, 50 ohm in and 50 ohm out with integrated functions such as bias controllers are another area. Again, this is an area where Renesas is really pushing the boundaries. DPD friendly designs, for easy linearization so that the DPD resources can be used sparingly and improve power consumption. Thermal solutions, as you can see, the EIRPs that we are pushing are pretty high, and the PAs can get pretty hot. So cooling technologies and thermal relief technologies are an area of innovation. And whatever you do, improving efficiency and lowering cost are critical. Similarly, on the small signal RF components, wideband devices, so that the skews can be minimized in the implementation, multi-channel integration and multi-band implementations, and multifunction integration so that the number of components in the RF front end can be minimized, and some unique architectures that can come in and help reduce hardware, such as phase shifters with switches to enable hybrid beamforming instead of resorting to digital beamforming all the time. On the RF transceiver side, I mentioned this a little bit already. Direct RF sampling is of extreme interest to our customers because this can provide a lot of flexibility in the implementation. And low power, high speed interfaces, especially with the chiplet architecture that I mentioned, die-to-die interfaces such as BO and UCIe become very critical. And implementing them with lower power consumption really helps, because the interfaces have become one of the highest power consuming portion of these chiplet-based architectures. Higher integration and chiplet architectures, like I mentioned, and power saving modes such as half rate, especially when we are talking about direct RF sampling. Similarly, on the DFE and the RU processor ASIC, any domain-specific processors with customized instruction set, and there are some companies which are innovating in this area. Optimized interface with transceiver, especially like I mentioned, the interface speeds are very high, and their power consumption is one of the biggest challenge. So implementing optimized interface bit with the transceiver and the RU processor is critical. Flexible L1 and software abstraction, I mentioned a little bit, and efficient DPD algorithms using AI and ML, and massive MIMO and multi-user MIMO beamforming algorithms. And like I said so many times, power consumption and cost remain critical for RAN implementations. Hopefully, I didn't go too fast, but I